Inside a single database, transactions feel almost magical. You can update multiple rows, and either all of the changes happen or none of them do. The database guarantees atomicity. But once your transaction spans multiple machines, that guarantee becomes incredibly difficult to maintain. Imagine transferring money between two banks. One database needs to debit an account, and another database needs to credit a different account. If the debit succeeds and the credit fails, money has effectively disappeared. If the credit succeeds and the debit fails, money has been created out of thin air. Distributed transactions solve this by trying to make multiple systems behave like a single database transaction. The most famous protocol is two-phase commit. It introduces a coordinator whose job is to orchestrate the transaction across all participants. In phase 1, called the prepare phase, coordinator asks every participant if it can commit the transaction. Each participant performs the necessary work, writes enough information to recover later, and replies with either yes, I'm ready, or no, I cannot commit. If every participant votes yes, the coordinator enters phase 2 and sends a commit message to everyone. Each participant permanently applies the transaction. But if even one participant votes no, the coordinator sends a rollback message and every participant discards its changes. The protocol sounds simple until failures occur. Suppose every participant votes yes, but the coordinator crashes before sending the final decision. The participants are now stuck in an uncertain state. They can't commit because they never received the commit message, and they can't roll back because the transaction might have already committed elsewhere. This blocking behavior is one of the biggest weaknesses of two-phase commit. During failures, resources can remain locked and progress may stop until the coordinator recovers. In large distributed systems, this can become a serious availability problem. That's why many modern architectures avoid distributed transactions altogether. Instead of trying to achieve perfect atomicity across services, they embrace eventual consistency using patterns like sagas and compensating transactions. Distributed transactions are possible, but the cost in complexity, latency, and availability often makes engineers choose a different trade-off.